Today we're working with binomial expansions. So binomials are those parentheses that have two terms in them. They could be z plus w like you see on the board. They could be a plus b. It could be 3x squared y minus 4z cubed. Anything that has two terms inside the parentheses. And then we are going to raise it to a power. Now, I don't know about you guys, but I'm pretty good at parentheses to the first or parentheses to the second. Even doing to the third, I usually take, like if it's x plus y squared, I'll usually take x squared plus 2xy plus y squared, and then multiply that by x plus y, distribute, combine my terms. If I needed to the fourth or the fifth or the sixth or the 12th, I'd have to keep doing another one of those xy parentheses times what I had before. A lot of distributing, combining terms, and that's a heck of a lot of work, right? Especially if I try to do one like parentheses to the 12th. I'm going to be at that for a long time. So what we're going to try to do today is to observe some patterns, see if we can figure out some patterns that will give us some shortcuts for expanding these without having to do all of that distributing. So I think we're probably all pretty good with these three. Parentheses to the 0, anything to the 0 is 1. A plus b to the first is just a plus b, and a plus b squared is a squared plus 2ab plus b squared. Are we pretty good with those? Okay, then if we wanted to get a plus b cubed, we know we could take what we had from a plus b squared and multiply that by another a plus b. So let's distribute the a, and we have a cubed plus 2a squared b plus a b squared. And then let's distribute the b, and we get plus another a squared b plus 2ab squared plus b cubed. And then if I combine my like terms, I'm going to have a cubed plus 3a squared b plus 3ab squared plus b cubed. So are we good with that? I only got some of this out of the way so it doesn't confuse us here in a moment. And are you willing to take my word for it that if I take what we see up here on the board now and multiply that by another a plus b in combined terms, we'd get this? And are you willing to trust me enough that if we take that times another a plus b and I tell you we get this, will you believe me? It's good because it's true. I'm not trying to mess you up. I printed. I'm not just trying to do, my thinking in my head, writing it down where you have to catch a mistake, because I usually end up making those. So now your job, look at these 6 rows that we have and start making some observations for me. There are a lot of things that you can see in that, things that are the same in every single one of them, or, oh, well, if you're on this row, you've got this going on. Just start noticing some patterns and some relationships, and raise your hand when you see one thing that you can tell me that you observe in that. Ian. Okay, excellent. So for the A's, I'll just look here at the bottom row. I start out with a to the 5th, and then I have a to the 4th, a cubed, a squared, a to the 1st, a to the 0. So the a exponents go down by 1 each time. Morgan, another observation. Okay, b's do the reverse. We start with no b's, b to the 0, b to the 1st, b to the 2nd, b to the 3rd, b to the 4th, b to the 5th. And that's true on the shorter rows as well, right? Okay, some other things that you can observe. What's something that you can notice in there, Gavin? Okay, so the coefficients of the second term go up, and what's more, could you make a prediction based on what you see here? What would be the second coefficient if I had a plus b to the 12th? So not only do they go up one each time, but the second coefficient is always the same as the original power on the binomial. So I've got a 2 right here. The original exponent was a 2. I've got a 3 for the second coefficient and a 3 for the power. Second coefficient is 4, the power was 4, and so on. Other observations? We notice that about the second coefficient from the beginning. Do you notice anything about the second coefficient from the end? Same thing, right? Because second coefficient from each end, 3s, 4s, 5s. In fact, do you notice any symmetry with those coefficients? 1, 4, 6, 4, 1, 1, 3, 3, 1. The left is a mirror image of the right on the coefficients. Okay, what else can we notice? Okay, I'm expanding binomials. I've got 2 terms in each parentheses. When I take it to the 0th power, how many terms do I have on the right-hand side? To the first power, how many terms? Second power, how many terms? Third power, how many terms? Give me a generalization on that. Elizabeth. Than the power of the binomial. So the number of terms is always 1 more than the power of the binomial. Okay, do you remember what degree means for a term? When you add up the exponents of each term? I want you to take a look at all of those up there and look at the degree of each term. Not the whole long string, but just each little term in there, and tell me an observation about the degree of the terms when you have the binomial to the 4th, or the degree of the terms when you have the binomial to the 5th, and so on. Hope. Okay, so the degree of each term is the same as the exponent on the original binomial. So when I'm cubing the binomial, this is degree 3. This one is 2 plus 1. This one is 1 plus 2. This one is 3. They each have degree 3. When I have to the 4th power, I have degree 4, degree 3 plus 1, degree 2 plus 2, degree 1 plus 3, degree 4. So the degree of each term is the same as the power on the binomial. So good job. I knew you guys could observe stuff and start seeing some patterns. Let's start making a list of these things that we've noticed. One exponent will increase and the other one will decrease. And in fact, we're going to be very specific about the order. If they put A first in the parentheses, A is going to be the one we start with, and it's going to decrease. We're not going to use commutative property and switch the order of these things around. We just noticed that the sum of the exponents is always the same, and it's the same as the power of the binomial. We also observed that there is one more term than the exponent. The second coefficient from each end is the same as the power of the binomial. So they all started with 1, a to some power, and so if it was to the 4th, it was 1, a to the 4th plus 4, something. The second coefficient is the same as the power of the binomial. We noticed a symmetry to all of the coefficients, and in fact, the coefficients are going to be the numbers in something that is called Pascal's triangle, and that is what we're going to write down next for your formula list. Pascal's triangle is going to take several lines to write it down, so don't start near the bottom of the front, and if you're nearly to the bottom of the back, be sure you're starting on a new page for writing down this formula that we are about to do for the numbers in Pascal's triangle, which are those symmetric coefficients that we were noticing in each of these expansions that we just wrote out. So let's turn to Pascal's triangle, and we are going to start off with 1, and then we notice that on all of those expansions they all started with 1 a to the something and ended with 1 b to the something. So we're going to put a 1 on each end of each row as we go along. So when I go to the next row, I need a 1 on each end. When I have a plus b squared, I have 1a squared plus 2ab plus 1b squared. Notice that 2 is 1 plus 1. If I add the two numbers that were up above it, I get 2. Sorry for my cough here today. Add a 1 on each end. Add the numbers up above. 1 plus 2 is 3. 2 plus 1 is 3. When I did my binomial expansion to the third power, I had 1, 3, 3, 1. A 1 on each end because we always start and end with 1 a to the something, 1 b to the something. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. If I go back to my fourth power expansion, it starts with 1, 4, and then 6, 4, 1. So it does match the pattern that we just wrote down. Next one should be 1, 5, 10, 10, 5, 1. Let's see if that's what we get. Add a 1 on each end. What's 1 plus 4? 4 plus 6. 6 plus 4. 4 plus 1. So we did get those numbers. Let's go on a couple more. If we wanted to take something to the sixth power, our row would start with 1, 6. What's 5 plus 10? 10 plus 10, 10 plus 5, 5 plus 1. Everybody see what I'm adding together to get the next row? Okay, one more for today. Add a 1 on each end. If we wanted to do the seventh power, we'd be looking at the 1, 7 row. What would come next? 21, and then, and then, and then, and then. Now I'm going to suggest leave a couple of blank lines in your formula list. So go ahead and skip a couple of lines and write 178 as a reminder. A few lessons from now, when they ask you for something to the 10th power, fill in the other rows that you need then, so that you've got it there. On a test, you're not going to be looking at your notes, but on a test, could you quickly write down Pascal's triangle to whatever row you needed? The 4th power or the 6th power or something? So you would recreate it, not sit down and just memorize it. You'd just be able to recreate it, know how it works and how to get it. Okay, let's now try to put this together with some expansions. So when we are expanding, we've got a binomial, 2 terms to a power. If it's to the 4th power, we're going to take the 1, 4 row. If it's to the 6th power, we're going to take the 1, 6 row, and so on. Those numbers will be the numbers that go in front of the terms all the way across. They'll be the coefficients. And then we'll take that pattern that we noticed, the first variable with an exponent that matches the power of the binomial, and then those first variable exponents are going to go down, and the second variable exponents are going to go up, and we'll have our expansions. So let's try a couple. So r plus t to the 4th. I know that that means I need to start with 1 r to the 4th. I know my r's then have to go down. R cubed, r squared, and r. My t's have to start with t to the 0 and go up. So t to the 1st, t squared, t cubed, t to the 4th. Do all of those have degree 4? Do all of those terms add up to 4? Yes? Okay, I want you to look at your 1, 4 row of Pascal's triangle. Since this is to the 4th power, we are going to have 1, 4. What's the next number on your 1, 4 row? And the next one? And the last one? And don't forget the plus signs in between there. And that's our expansion without having to do all of that distributing over and over again and combining like terms. Kind of nice, right? This is actually the first of 2 shortcut methods we'll learn this semester for this. We'll have another one coming up down the road a little bit. Okay, let's do another one where we are expanding one all the way out. This time, let's go farther. We're going to have 7 terms because it's going to be the binomial to the 6th power. So we have z to the sixth, and then the z's are going to go down, and the w's are going to go up. I get all of them in there the way we needed them. I get my z's decreasing, my w's increasing. Do they all add up to 6 each time? Okay, I need you to go back and look at your 1/6 row of Pascal's triangle. Since it's the 6th power, we're looking at this 1/6 row. So we need 1, 6, 15, 20, 15, 6, 1. Put those in front. 1, 6, 15. Was 20 next? 15, 6, and 1. I don't really need the 1. I can just use the invisible 1 there. Because this was plus, I have pluses between all of these terms. And there is my answer for this problem. Any questions on that? Still got some other things we're doing with this stuff. I want to caution you, you're not going to have this just yet, but coming up a few lessons from now, they're going to start doing a minus sign in here between instead of a plus. So when you have z minus w, that's z plus a minus w that all got raised to the power. So that means everywhere you see a w and what I just wrote down, it's now going to be a minus w. So here, if this was a minus w right here, that would have become a minus 6 out in front. But for the next one, if I had instead of w times w, if I had minus w times minus w, that minus minus would still be a plus. And so on across that. So that kind of makes sense. You don't have to really worry about it a lot yet, but just a heads up, that's coming. After you've then had a few of those, they're going to change it and maybe have a 2z instead of just a z. Or maybe have a 5x squared wz cubed for the last term. If they had something like a 2z instead, that would mean instead of z to the 5th, I have 2z times 2z times 2z times 2z times 2z. So I would have had 32 z to the 5th. Still, then 32 times 6, I'd have to simplify that. And so on across there. So just a heads up that they are going to get them more complicated. Now, the other thing that we are still going to do today, many times they will ask you to write out the full expansion of one of these binomials. Other times, they just want the 3rd term or the 7th term. We could go through and write out the whole thing and then count across to whichever term we needed. But that's a little bit of a pain if it's x plus y to the 12th to do that whole expansion when we only needed 1 term. So I want us to look at this and see if we can start kind of figuring out some shortcuts of how we could get that term. Now, we have to be careful. This is the order we're doing it in. If they put, let me get rid of this too so that doesn't mess us up here later. If they have z first in the parentheses, that means your first term is the z to the 6th one. You don't get to turn it around and start with w to the 6th and go backwards. Because when they are doing that, this needs to be your first term, your second, your third, your 4th, 5th, 6th, and 7th terms. So let's start off by taking a look at, maybe we'll take a look at this 3rd term right here. And let's see if we can figure out how we come up with that. I think it's pretty easy to say that the coefficient is just going to come from Pascal's triangle. So for the coefficient, we're going to say, oh, which row do we need? So in this case, we need the 1/6 row of Pascal's triangle. And if we want the third term, we just need the third number in that row. And that's how we'd come up with the 15. Everybody good with that? If we look at, since it's to the 6th power, we look at the 1/6 row, and it goes 1, 6, 15 is the third number in that row, so that's the number we're going to use. And then we know, since it's Z and then W, we're going to have some Z's and then some W's in our term. But we've got to figure out a shortcut to get the exponents without having to write the whole thing out. And I'm going to give you a hint. It is easiest to get the last exponent first. So I want you to look at the last exponents of all of these terms, and let's see if we can come up with a pattern for them. In the first term, it was W to the 0. The second term is W to the 1. The third term is W squared. The fourth term is W to the third. The fifth term is W to the fourth. The sixth term is W to the fifth. The seventh term is W to the sixth. What is the relationship between the term number and the exponent? Giselle?
Whatever term it is minus 1.
So this is going to be the term number minus 1. So since we want the third term minus 1, we need a square after the W. To get the final exponent, do you remember our observation about the degree of each term? Hope? The two of them together have to add to the binomial's power. So in this case, they have to add to 7. So I just take 7, or sorry, they have to add to 6. So we take 6 minus 2, and this exponent has to be 4. So without writing all of that out, I could have come up with 15 z to the 4th w squared. So I want us to do a couple of these with the shortcut way of getting just the term they ask for, and see if we can make sense of this. So I want the fifth term of j plus k to the 7th. So which row do I need to go to on Pascal for the numbers? I need to go to the 1, 7 row of Pascal. And I need to look for which number in that row? I need to look for the fifth number in that row. And what is that going to be? So 1, 7 row is this last row that we wrote down. 1, 2, 3, 4, 5. So this 35. My variables are j and k, so I know my term has to have some j's and k's in it. Do I get the j exponent or the k exponent first? So we're going to get the k exponent first. And how do I get that exponent? Ian? So the fifth term minus 1 means that needs to have a 4 on it. And finally, how do I get the j exponent? Casey, you remember how we got the j exponent?
Yeah, I would do the second as the exponent minus 4 when
So the exponents have to add to that power of the binomial. So in this case, we are just taking 7 minus 4 gives us 3. And there is our fifth term of that expansion without having to do very much work. Kind of nice. One more, and then we'll get going on homework. So this time, let's do sixth term of s plus t to the 6th. So which row of Pascal? So the 1/6 row. Which term do I need in that row? So you guys look at your 1/6 row and count over what is the 6th term in that row. Sydney, what's the 6th number in that 1/6 row? So that's our coefficient. This has to have S's and T's in it. Ariel, am I going to get the T exponent or the S exponent first? And how do I get the T exponent? So I'm going to take this term, -1, so 6 minus 1, that needs to be a 5. Callum, what about my T exponent? My S exponent, thanks. Why does it have to be 1? So the exponents have to add to this 6. 5 plus 1, which I can write, or I can leave it the invisible 1 in there. Any questions on what we've talked about today?